We're ready to compare statistical learning estimators. In the previous videos, we've introduced this problem where we're estimating the mean salary in 2023 among Major League Baseball players whose 2021 salary was between $5 and $10 million. We proposed three estimators: the average salary among sampled players who fall in this target population, the predicted salary among all players in that target population from a regression model learned among our sampled players, and that same predicted regression value from a machine learning model. We'll now talk about how we could compare these three estimators. We're going to think in terms of what's known as bias and variance. So looking at this middle estimator, we have a bunch of sample estimates arranged vertically. So each dot corresponds to the estimate we make when we draw a particular sample of Major League Baseball players. These sample estimates are not all the same value. Depending on who we get in the sample, they're different each time. This is why there's a variance in our estimates. They're arranged vertically up and down a little bit. There is also bias in our estimates. In this case, the line is perhaps not the best approximation to this conditional expectation function, the response of 2023 salaries to 2021 salaries. In this case, our estimates are all a little bit below the true target population mean. So this is what we'll call bias. Now, before I get to math, I want to introduce some notation. Let's call the true target population mean theta. That's the Greek letter theta, T-H-E-T-A. Theta is the average value of 2023 salary for all the dots in this vertical slice, both the blue dots and the gray dots. It's the thing we're trying to estimate. Theta hat is any particular estimate. So theta hat, like this little dot down here, is what we estimate when we draw some sample from that population and apply our learning procedure to that sample. The third quantity we're going to need is the expected value of theta hat. This expectation operator E just corresponds to an average. So here theta hat is a random variable. It has variability because of who happens to be included in the sample. The expected value of theta hat is the average value that this estimator will take when applied to many repeated samples from the population. Bias is the difference between that expected value and the true quantity that we're trying to estimate, and variance has to do with the difference between particular sample estimates, theta hat, and their expected value. Okay, we're ready for some math. So let's think about an error. This is the difference between the estimate, theta hat, and the true quantity, theta. Here I've just broken that out further by subtracting and adding the expected value of theta hat. So I've just basically added 0 here. This says that any given error, like the difference between theta hat and theta, that's the difference between theta hat and its expectation plus the difference between the expectation and theta. So let's just square all these terms. So what's happened here is that I took the left side and squared it. Then I've squared each of these, and I've added this funky looking term at the bottom that's going to end up being 0. You know from algebra when you take the quantity a plus b squared, it becomes a squared plus b squared plus 2ab. And that's what's happened here. We have a squared plus b squared plus 2ab. So the reason we're squaring this is that we want to think about errors in kind of an absolute sense, where they're going to be positive whether they're negative or positive. So next, we're going to take the expected value of these quantities. We want to know, on average over repeated samples, what's the squared difference between the estimate and the truth? How can we think of that in terms of bias and variance? So all I've done here is add these expectation operators. We took the expected value of the left, and on the right, I added it to each of these terms. Now that might look complicated on the right, but basically I've said if I have a plus b plus c, then the mean of that is going to be the mean of A plus the mean of B plus the mean of C. So a last step here that I'm not going to go into detail on is that this third term is 0. You can prove this using the law of iterated expectation conditioning on the expected value of theta hat, but that's just a bunch of gobbledygook, and it's not really important for building intuition here. What's important is that we can drop this third term and focus on the 3 terms at the top. So we have on the left our expected mean squared error. So this says, on average, across repeated samples, what's going to be the squared difference between our estimate, theta hat, and the truth, theta? we would like the mean squared error to be small. A good estimator is going to be one that has low mean squared error. Now, this first term in the decomposition of mean squared error is variance. This is the expected value of the squared difference between theta hat and its expectation. That's a mouthful. So what does that mean down here in the figure? That means on average, over all these sample estimates, what's the squared difference between the estimate and the average of the estimates? This tells us sort of how spread out these points are here. The variance of this estimator is going to be much bigger than the variance of this estimator. The third term here is bias squared. So we have the bias. This is the difference between the expected value of the estimator and the truth. Down here in the figure, the bias is the difference between this expected value, the average of the points, and the true thing we're trying to estimate, this horizontal line. If you take that difference and square it, then you'll get the bias squared, which is this second term in the decomposition. As we compare estimators, it's often useful to think in terms of mean squared error, variance, and bias. This is because sometimes we'll take an estimator where we're actually willing to accept some bias, like this biased estimator here based on the linear regression model, because it might be a much lower variance estimator than the unbiased estimators that are available to us. If our goal is to have an estimator that's close to the truth on average, that has low mean squared error, then we have to do some kind of balancing between bias squared and variance in order to minimize that mean squared error. In the next video, we'll talk about a few learning algorithms.